torn lucky ticket. So the input is an array of strings where each string is at length at most 5, and they only consist of digits 1 through 9. So an example input would look something like, let's say 5, 69, 420, 1, 4, 3, 6, and 21. And this is like n equals 5, because there's 5 of these strings in total. And the goal of this problem is to count how many pairs exist such that if a pair is a concatenation of these two strings, it's an even length string, and the sum of the first half of the digits is equal to the sum of the second half of the digits. So just in general, when you encounter a problem that asks like how many pairs exist such that the sum of these pairs meets some sort of criteria, or this pair meets some sort of criteria or whatever, you always want to try to think of how can I solve this using a map. In this case, let's consider string A as our first half of a string and string B as the second half of a string. So the n-squared solution would obviously iterate over every possible pair of A, B, concatenate them together, and then find the sum, right? But that's inefficient, and the most obvious way we can optimize this is to note that the only thing that matters, well, there's two things that matter. What matters for string A to match to string B is the digits of string B, or specifically the sum of the digits of string B, as well as how long string B is. So let's let L at A and L at B be equal to the length of string A, and L at B is the length of string B. So if L at A is equal to L at B, this is a pretty simple case because all we care about is the sum of digits of A to be equal to the sum of digits of B. And we can store that in a map by iterating through all these strings, and then for each length, create a map that stores how many strings have some certain sum. And this is a pretty straightforward case. The second case we need to consider is if the length of string A is less than the length of string B. Now this is going to be a little trickier because we want to have the string B be pre-processed so that when we iterate over string A, we can directly retrieve that information from the map. But how do we do this? Well, I'll give you an example. So let's say the length of string A is equal to 2, and the length of string B is equal to 4. So we have some digits like A1, A2, and we also have the digits B1, B2, B3, and B4. And the goal is that we want to make the sum of A1, A2, and B1 be equal to B2, B3, and B4. Well, this statement is actually equivalent to checking if A1 plus A2 is equal to B2 plus B3 plus B4 minus B1. And the reason why we do this is that we want to move all of the A terms to one side and all of the B terms to the other side. Because when we create the map that stores information about the strings B, we only have access to B values. So we want to put this value into our map. That way, when we iterate over string A, this is the value that's stored in the map, and if these match, then these form a valid pair, and we can add that contribution to our final answer. Now, the trickiest step, or the trickiest case to consider is if LA is strictly greater than LB. Say in this case, LA is equal to 3, and LB is equal to, say 1. Then the concatenation would look something like A1, A2, A3, and B1. And the string is a valid pair if A1 plus A2 is equal to A3 plus B1. But the problem now is that if we want to we can contribute the sum of B1, but in our map, well, you can actually store a different map for every possible length of string, because the lengths of strings are only from 1 to 5. So in other words, LA is bounded between 1 and 5, so it is actually a feasible solution and would probably work if you just stored a map for every possible different length, in which case you can just treat this case like a little more straightforwardly, and it would work just fine. However, if you want to just use one map to store all of this information for one LA, instead of storing 5 maps for each possible length, you can store one map for each possible length by just reversing the string. So what this means is that if we reverse this, B1, A3, A2, and A1, the condition that we're checking for is exactly the same, except now we've transformed this case into the LA less than LB case. And the reason why this is useful is that this basically means that we can compute these two cases first using just a map, and then we don't have to make any modification to the first string that we put in some pair A. And then if you want to calculate this set of answers, we can just reverse every string in this initial array and run the same algorithm that we did to run this case. And then any pair that used to be LA strictly greater than LB will now be transformed into LA is less than LB. And then the code we can use is exactly the same. And then the sum of all 3 of these quantities, or the number of pairs that fall under these 3 quantities, is going to be our final answer.